Welcome to Future Consideration in MIDD. We'll look at artificial intelligence and machine learning and how AI and ML can be applied to MIDD. Divided into three sections. The first one is introducing AI ML, looking at the landscape and what are the different components of AI ML, specifically focusing on MIDD. Section 2 would be the regulatory viewpoints and applications in MIDD. And in section 3, we would focus more on deep learning basics and then look at different resources that are available that could help you learn more about how you could build your own models and apply in your use cases. Looking at the definitions for AI, ML, and deep learning, AI as a concept is where a machine can mimic human intelligence with the ability to predict, classify, learn, play, reason, and perceive. Within this larger field of AI is the machine learning field, which is basically incorporating math and stats into an algorithm that can learn from data and improve its experience. And you might have heard of big data and how that's being leveraged through machine learning to build models. Within the field of machine learning, there's deep learning, which is essentially based off of multi-layered neural nets, and these learn from vast amounts of data to solve complex problems and challenges. One advantage of deep learning is that it can handle multiple modalities, and these can include image, audio, video segmentation, classification, and we'll learn a little bit more around the applications of deep learning in different areas. Now, briefly looking at traditional machine learning and deep learning, it's only relatively recently that deep learning is seeing a lot of interest given its flexibility to handle multiple modalities and combine multiple modalities to perform the analysis. If you look at traditional machine learning, these algorithms can include decision trees, support vector machines, ensemble methods like boosting or random forest. Traditionally, there has to be some pre-processing step that needed to be done prior to applying these methodologies, and that was due to the curse of dimensionality, where we had to reduce the number of features before applying the machine learning algorithm. When it comes to deep learning, we can circumvent that process and provide the data to these deep learning models, and this can include feed-forward network, convolutional network, or recurrent networks without having to perform some of the initial steps. And we'll learn a little bit more as we progress through this chapter. And briefly looking at the evolution of deep learning, there has been a lot of work that has been done since 1940s, but I want to highlight a few of these algorithms that have been key in essentially pushing forward the field of deep learning to be applied in MIDD. The first two I want to highlight is the RNNs and bidirectional RNNs. So these are recurrent neural networks, which gives us the ability to perform time series analysis. And more recently, a lot of work has been done in applying LSTMs, which are long short-term memory units, to model time series data that span over a wide range or a time. Another example is in image analysis, and a lot has been done in image analysis. One example is LeNet, and the other is GANs, which is generative adversarial networks, and these essentially can help generate synthetic data that could be used for research, especially when there is restrictions with data sharing. When we specifically look at the machine learning methodologies and algorithms, at a high level, machine learning can be divided into two groups, supervised and unsupervised. And within supervised, there are different ways of working through the data in your use case. So I was mentioning deep neural net where you have algorithms like convolutional neural nets to handle image. Time series data can be handled using LSTM, or recurrent neural networks, generative adversarial networks can be used for synthetic data generation, perceptrons, and autoencoders are some other examples. There are other more traditional methods that some of you might be familiar with, like regression classification, which include linear regression, logistic regression, and so forth. And there are other ensemble methods like random forest bagging, boosting, which I briefly mentioned before. On the unsupervised side of things, there is clustering, and there are several different algorithms that can be used for clustering analysis. There is dimensionality reduction, and there is pattern search. I won't go into too much details, but there's a lot of information available in the link that I provided here. Now, looking at machine learning or deep learning approach compared to more traditional modeling and simulation, in a more traditional modeling and simulation approach, you would find data being used with a particular program, and using the computer to process the data, you will get an output. However, when you look at machine learning, it's fundamentally different in the sense that you would use the data and the output along with the computer to generate the program. Basically, the algorithm is training itself using the data that you provide. So in terms of AI ML modeling strategies, we can look at it from the output type. So a lot of times you might have a continuous output. This could be biomarker information, or say blood pressure. You're trying to predict blood pressure or temperature. This type of output, usually we use regression. There are multiple examples. Some simple examples are linear or polynomial regression. You could use more sophisticated methods like deep neural net as well in this case. But there are other output types like classification, right? Where you have different classes. It could be tumor, not a tumor, or another example could be if somebody you want to predict if somebody would improve based on their baseline characteristics. So in that case, we do classification, and some examples there are decision trees and deep neural nets. Clustering is another type of output that you might want sometimes when you have, say, unsupervised learning example. And here, a good example typically used is k-means clustering. There are other examples that I showed in the previous slide. The last one I have here is looking at patterns, and through pattern recognition, this could include support vector machine and convolutional neural net, which is a type of deep neural net, and we'll briefly look at that in a subsequent slide. There are several modeling considerations when it comes to AI and ML. The concept of garbage in and garbage out applies quite well in this case, and this is a good representation. If your data is garbage but your model is great, your results are going to be garbage. On the other hand, if your data is great but your model is garbage, your results are going to be garbage. So something to keep in mind. Interpretation is important. So to apply the right algorithm, we need to understand problem statement, and most likely you would benefit from having a domain expert that has the understanding of the disease on your team, and that would cut a significant amount of work for you in terms of identifying what are some of the important features that you would want to ensure it's part of your analysis set. The second one is no free lunch. So there's no one single model that can be used for every problem, and most likely you would need to use multiple algorithms and find the one that works for you. The last one is debugging errors. In here, given the complexity of these methodologies, it could be challenging to debug errors. So it is very important to ensure that when you are building these models, you are following good modeling practices. This could include developing models in a modular fashion, or making sure that you're providing enough annotations to the code. I want to switch gears a little bit and talk about the concept of black box. A lot of times, deep learning models have been considered as black box given the complexity. And we see that under GDPR, the right to explanation, they mention that an individual has a right to get explanation of the decision reached for their case. So I want to take some time to look at different ways of exploring what the model is doing in terms of coming up to a prediction. There are three ways we could look at the interpretation for a machine learning model. First one is probing, where you inspect the inner logic of a trained model. For example, how a certain feature is responsible for prediction. There are different ways to do that, different components within a neural net, and we'll go in a little bit more detail there. Second one is perturbing. So here you would perturb the input data. For example, you could remove a feature, perform sensitivity analysis and what if analysis. So here you would see perturbing the input data, how does that change the output? And finally, looking at surrogate model, where you would try to use a more interpretable model. So this could be a decision tree model or logistic regression, so forth, and try to see if you can find some explanation of the predictions that the black box model does using the surrogate model. So probing, there are three approaches: weight-based, gradient-based, and activation-based. So weight are essentially the strength of a signal between two neurons within the neural net, and we'll go in more details of the components for a typical neural net. But for this purpose, when it comes to probing, we can look at the weight or the strength between different neurons to see how that affects the outcome. The second one is gradient, and the gradients are used for training the model, and we can use gradient-based method or probe based on the gradient to understand what the model is doing. And then activation-based, essentially looking at when you use the extent of activation, how does that relate to the output. And we'll go in more details when we look at the basics of or building blocks of an ANN model. But for now, when it comes to probing, you could use these weight-based, gradient-based, and activation level-based approaches. Second one is perturbing. It's pretty straightforward. Essentially, if you see different instances are different here, shown as different sequences. You have GT, CA, and so forth. And in the first example, you do a leave one feature out sensitivity analysis, see how leaving that particular feature, or the third feature in this case, is changing the performance. And you could see if that's an important feature when it comes to making a prediction, and it would change from your problem statement. So you might be looking at something else. In that case, feature number 3 might be important. In other problem, it might not be important. So you want to be able to associate how the model, what the model is doing, and which features are critical for a certain prediction. The other similar example is to look at permutations. So essentially, you would change feature 3. So here is an example where you change C to G, C to T, and so forth, and see how that affects the performance of the model. The last one is using a surrogate model, and this is pretty straightforward. So what you want to do is train a model that is more interpretable, and that would approximate black box model. This might not be as easy as it sounds. Some examples here are simple linear models or decision tree models. I do understand that compared to a more complex deep learning model, these models are simple, and that's sort of a limitation here. But the idea is to train the model with input and prediction from the black box model, and If you find that your surrogate model doesn't completely help you with interpretation, you could use it to learn a portion of the black box model. There are other more sophisticated methods like SHAP and LIME. LIME is the local interpretable model agnostic explanation method, which would help look at certain parts of your neural net to see what it's doing. I won't go into too much details. If you look at the link that I provide at the bottom, you can find more information there. But the last point here is you could do things like figure out why some patients are misclassified as surviving after cardiac arrest. Right? Your black box model might be doing really well, but you want to understand for cases that it's not doing well, what is the reason behind its misclassifying. Next, let's continue the discussion and look at some knowledge gaps and pitfalls. The first one is the notion that more data will solve the problem. This is true for most cases, but a lot of times there are low quality data or irrelevant features that would hurt you more than help you because you are training with noise and not signal. And we'll go in more detail in our next point here. And then the second point is the model might be underfit. Essentially, here adding more data is not going to solve your problem because you need to use a different model, a more complex model, to be able to improve performance. Second point is generalization, so training on noise versus signal. And a good example is here on the right, where unfortunately all the data set that we have in this case, where you're classifying a horse, if a horse is in a picture or not, had these tag to show the source, and the figures that didn't have horse didn't have this tag, and the model learned not to classify the horse but to classify whether the tag is present or not. So it's essentially training on noise instead of training on signal, the signal being the horse. The second one is unrepresentative data set. Not much to say there. If you are using data set that doesn't represent what you would see in reality, there's a very high chance your model is not going to do well. Train test leak, this is important. Very obvious, but important, and the idea here is to ensure that none of your samples, instances that are used to train the model leak into the test, and this could cause erroneous prediction. And the last one here is changing data generation process over time, and this is an important one in the sense that over a period of time, there are different methods, equipment that are used to capture data. A good example could be maybe a thermometer, where technology has evolved to be more precise in terms of the temperature we measure. And it might be so that in your case, your model is very sensitive to maybe the temperature values, and it needs to be very precise. So in that case, you have to be careful how it was captured. The third one is system level performance, and I briefly mentioned this. If you have faulty input with a perfect model, you're going to get wrong prediction. Pretty obvious, but very important. The last point is performance is not everything. Although we harp on the point that we want to achieve maximum performance, but we also need to be mindful of whether we are missing any clinically relevant factors. So this can cause clinical meaningful failure. So for example, your model might be doing very well for cancer subtype classification, but it might be missing rare but aggressive cancer type, which you might not know unless you take into account or involve a subject matter expert, an oncologist in this case. So something to watch out for that. The next thing to watch out is demographic bias. A lot of times the model would not be able to detect bias, it would train on what it sees, and it is on the modelers. It's modelers' responsibility to ensure that there is no demographic bias. So, for example, there could be inaccuracies in connecting quality of life to socioeconomic status, right? So, for example, prediction of quality of life can be highly weighed on the socioeconomic status. The last one is quite important but not discussed enough, is the violation of regulation. And in this global environment, we have to be very cognizant of regulations. And one good example is discriminatory biases in the data for training. So essentially, if you're training something in the US and using it in, say, Europe or China or somewhere else, where the regulation is totally different, you're on the hook for what your model is predicting, and if the consequences could be dire. So something to keep in mind. Let's look at some solutions. I've already highlighted a bunch of them, but I don't want to go into more specific, because this might be quite helpful when you're building your own model. So the first one is build your model through iteration. Pretty straightforward. The strategy here should be to start with a model that's simple and add complexities. A lot of times you want to test different architectures and see how the performance is, and then iterate as you go. Definitely a wise move to have domain experts on your team to get their input. It would save you a lot of time and also make your model more generalizable, more representative of the problem statement that you're looking at. Third one is to use software experts, and this one is essentially thinking about what the package would look like, not just the back end but also the front end. It's very important that when you develop a model, it's easy to use, and working with software experts would help figure out the best use for your model. Fourth one is to incorporate model explainability and interpretability. We discussed that, some strategies there, and it's definitely something that needs to be front and center as we are using more and more data and more complex models to answer more complex questions, right? And it's it becomes very difficult if we don't look at model explainability and interpretability. Fifth one is performance validation. Nothing more to say there. It's essential to test your model on unseen data. If you are lucky enough, you will have data maybe from a different source itself, different location, just to really test the robustness of your model. Sixth one is to look at subgroup performance. I briefly mentioned about the cancer example. It's essential to check on subgroups to ensure that your model can be generalized to that subgroup. And then finally is to create data set thoughtfully. A lot of times in AI, ML, the data sets are not built for AI and AI ML analysis. It's secondary use of data in the sense of performing the analysis, and it's very specific to the problem statement. You might use a different cut of the data or analysis set for one problem, maybe a classification problem, or looking at maybe a biomarker A versus maybe a regression problem, looking at a biomarker B, right? So it's essentially combining some of the things I mentioned in earlier points to come up with data sets that are more thoughtful, so that you can get better performance and be more generalizable and be more clinically meaningful. Let's go on to section 2. Here we'll look at AI ML landscape in pharma, and also look at some specific examples and how AI ML is being used in model-informed drug development. So first, let's look at some regulatory viewpoints, especially around FDA and EMA. Within FDA, it's primarily being used in CDER. There has been a guidance titled Software as a Medical Device. Within the drug development space, CDER has not yet formalized that guidance. On the EMA side of things, there has been the new regulatory goals for 2025, which has highlighted the use of AI/ML And I want to read one specific quote from the regulatory science document from EMA, where they say, exploit digital data and artificial intelligence in decision making, which indicate that they are interested in incorporating the use of AI/ML within the regulatory space. Looking at a little bit more detail around where AI/ML is being used, and you'll see that majority of it is in the preclinical space. There is a large focus of use of AI/ML in the discovery space, specific to the structure of the molecule. So in the QSAR space, the key driver here is data availability, and also there's less regulatory scrutiny in the preclinical space. When we move to clinical space, this is still emerging, and there needs to be identification for fit-for-purpose application. Some of the challenges here are, of course, the data quality and quantity, and there is high regulatory scrutiny when it comes to the clinical side of things. Looking at a little bit more detail at the fit-for-purpose approach, the application of machine learning in MIDD needs to answer the three questions. What is the drug development need? What methods are most appropriate to address this need? And what data can be used to support these applications, these ML methods? So something to keep in mind as you develop or review applications that have ML methodologies being used. So looking at what we are seeing currently within the submissions that are happening, most of them are exploratory analysis or part of a larger analysis, mainly focusing on clustering patients into subgroups with different risk-benefit profile, also looking at association between drug response and baseline factors. Besides research, it's also being used for review operations. Some other examples that I found in literature is drug exposure response analysis, time-to-event analysis, and I've put the link here at the bottom of the slide if you want to look into more details there. Ultimately, the key considerations for use of AI/ML in a regulatory setting is definitely fit for purpose, generalizability, interpretability, and explainability. And the final point we have highlighted, discussed. So next, let's look at some applications. I have created this table to provide the area of application and a little bit of description. I have some more examples that I want to go in more detail to highlight some algorithms that are being used for specific use cases. So the first example here is in drug physicochemical properties. Here, the authors have used a random forest to predict solubility of a potential drug candidate. Second example is population PK. So the authors here have used evolutionary search algorithm to pre-screen covariates in population pharmacokinetic analysis. And this is a good example of using a hybrid approach where you are basically looking at different covariates and then doing a, say, a dimensionality reduction, or reducing the number of covariates that you have to deal with when it comes to your PopPK analysis. The third example here is outcome prediction. The authors here were successfully able to perform an analysis where they could predict success or failure of clinical trial by different compounds that have unfavorable toxicity properties before they conducted the clinical trial. The final is the drug repurposing example, and here the authors used machine learning to find novel indications of existing drugs, and we are seeing more and more of these type of drug repurposing examples. Looking at some other examples, and I want to go in a little bit more detail in these to highlight the algorithms that were used for these examples. The first one is drug-drug interaction. So here the authors created something called a deep DDI, which is essentially a deep neural net for drug-drug interaction. They've trained a deep net model with 192,000 or so DDIs to predict drug-drug-drug food interactions for prescriptions and provide dietary recommendations and new molecules. The authors also did was they were able to create the model to provide guidelines for adverse reactions as well as provide in textual form what the recommendation is. The second example here is a pharmacological anemia management, and here the authors use reinforcement learning to personalize pharmacological anemia management. A little bit background on reinforcement learning. So this is agent-based learning where the agent interacts with the environment to maximize its reward. In this case, particularly in this example, the authors use something called a Q-learning algorithm, which is an off policy, which essentially means that the agent would take random actions to find the best path towards the outcome by the goal is to maximize the reward there. The third example I have here is in glucose control. The authors created a closed loop glucose system, and they compared a conventional glucose control system to one that combines mathematical model, glucose sensor, and reinforcement learning model. And I briefly talked about reinforcement learning. And they ran a clinical trial, which was multi-center open label randomized trial for adults that have type 1 diabetes for 2 or more years. And they compared these patients who were randomly assigned one of the two systems, the one which was deep learning based, the other was sensor assisted pump therapy for 12 weeks. And then they basically found that the folks that were on the deep learning based system, they did better in terms of having their time within the target range. The last example I have here is in Alzheimer's disease, where the authors used conditional restricted Boltzmann machine to create digital subject that are statistically indistinguishable from the actual control. And this is a very interesting application which can have a lot of use cases in terms of creating a data set that could be shared, which is typically restricted from sharing, or looking at maybe potentially synthetic control arm. Next, let's look at use cases in a different angle. Here I'm showing how a particular type of data combined with a certain algorithm can be used in an application. So, for example, if you have EHR record, which has text data, and this could be physician entered notes, you can use natural language processing to understand signals of which drug is working, which drug is not working. Especially this is being explored in COVID-19 for drug repurposing. So that is one use case for that. The next one is what we typically see is longitudinal data. And here you can use LSTM, which is long short-term memory transformers, to essentially do disease progression forecasting. Third one is imaging, and here algorithms like CNN, convolutional neural networks, can be used for segmentation, disease state classification. And you can combine imaging data with longitudinal data or EHR data with a set of different algorithms to do multiple things or be able to capture more sources of variability. The final type of data, clinical data, of course, and more specifically clinical data that has a lot of restrictions in terms of sharing it. In that case, we could use something like a generative adversarial network or restricted Boltzmann machine to create the synthetic version, which would ensure the quality and the correlations between the different features. And that can be used to share and do research on without having to go through the restrictions with data sharing. So next, I want to briefly show you CNN, which is slightly different, but has an important application in terms of analyzing images, which is typically not possible through traditional homomorphic methods. So here, essentially, one example is you'll be able to take in input as an image and do, as for example, classification in this case. The other input that you can provide is through spectrograms, which can be used as input for, say, classification or some other task. You can do segmentation of cortical regions that are of interest. So let's move on to section 3, which is the deep learning basics and resources. So far we have looked at what is AI ML, what is a landscape, and how AI ML can be used in MIDD. Let's just look at what are the building blocks of deep net models, and then I would finally provide some resources for you to explore and to look into, improve your knowledge. So at a granular level, deep nets are essentially artificial neurons connected with each other. So here's an example of a 2-layer neural net. Essentially, the way we count the layers is all the hidden layers and the output layer. So the input layer is not counted as a layer. If you look at deep net, which is essentially if you have more than 2 layers, you can term it as a deep net. Here you would see we have 5-layer fully connected neural net, and it's fully connected because you would see that each neuron, say for example in a hidden layer, hidden unit is connected to all the neurons in the previous layer, and the information flows from left to right. So as I mentioned, the neural net consists of building blocks or artificial building blocks, which are essentially neurons, which are inspired by the biological neuron, where you have information coming from the dendrite into the nucleus, and when it crosses a certain threshold, the signal would go through the axon to the next neuron. Similarly, in an artificial neuron, you have information coming from the other neurons, or in this case, let's say input, with a certain signal dictated by the weight, and all these inputs go into the neuron. There is a mathematical formula for calculating the sum of the input signal and the weight, and a bias is added, and I'll go into more detail what that looks like in the next slide. And then you apply an activation function to get you an output for that particular neuron, and this you could see is one part of the whole network, and this output is fed into the next subsequent layer. As I was mentioning, there are 4 things to remember here. The first one is input, which is the data that's fed into the input layer, and the second one is weight. So this is the weight associated with each of the connection, and this determines the strength of the connection. There's a bias, which is essentially added to ensure that when you sum the weights and the input, it crosses a threshold, and the activation function, which determines the neuron whether it will fire or not. And when you put all that together, you'll see that in this equation you have your weights times the input, which are summed up, added to a bias, and applied to activation function. Go in more details around the activation function in subsequent slides. But in practice, when you look at how this is implemented in, say, Python or R, typically you generate a matrix for input and the matrix for output, and then when you want to do the summation, you would just do the dot product. As I was mentioning, activation function is an important component in neural nets. There are multiple activation functions that you can use, and there's also combinations of activation functions you can use depending on your use case. The first one is sigmoid, which is essentially an S-curve, quite common. A lot of you might have used it. It's non-linear. It has a smooth gradient. The output is between 0 and 1. And it's typically used for output layer for classification problem, right? Either say improved or not improved or some other classification. The drawback here is that there is vanishing gradient if you use sigmoid. Essentially, during training process, when you are calculating gradient, the bigger your network is, the gradient would essentially cease to exist if you're using sigmoid function. The other drawback here is that it's not zero-centered, which might be important in some cases, and essentially having zero-centered makes it easier for model input to have strong negative, neutral, or strong positive values, which would help in model training. So quickly going back to the vanishing gradient, you could see that the gradient around the top or the bottom of the S-curve would essentially be flat or zero. And you can imagine that as the model gets trained in the backward propagation step, we would lose that gradient, and that would cause the model to not get trained properly. The second example here is tanh. It's similar to sigmoid function, but it has an advantage of being zero-centered, but it also has vanishing gradient problem, and it is computationally intensive. The commonly used activation function is called ReLU, which is rectified linear unit. It's non-linear. It's pretty straightforward. It is computationally efficient because it is essentially, if you have a value greater than 0, that's the value you would use, and if you have a value, output value, which is less than 0, you would use 0. However, there is an issue with dying ReLU problem, so which is essentially if your input approach is 0 or a negative value, then essentially the gradient of the function becomes 0, and this would have issues when training a model. So what we do is have a very small value instead of having 0, which is called leaky ReLU, to mitigate that issue. There's another activation function called swish, which is a relatively new self-gated activation function by Google. The equation looks like sigmoid with z in the numerator. It has better performance than ReLU. It's being explored, but usually what you would see in practice, ReLU is the one that's used for all hidden layers. Now let's look at how we can train a neural net. The first thing we do is to initialize the weight and bias matrices. What we want to do here is to randomize the weight and bias values between 0 and 1. Next, we will define the activation function. So typically, as I mentioned before, we use ReLU for hidden layers, and then for output layer, depending on your use case, if you're doing classification, for example, you want to use softmax for multi-class classification, or use a sigmoid if you have binary classification. For regression, you could use a simple linear model or linear activation. The third one is forward propagation, where you calculate the output for each neuron, which I mentioned earlier, the y cap values by summing up the weights and the multiplying the weights to the input, and then adding the bias, and then running the activation function through it. And you would go from left to right to the forward propagation, and then you would calculate the loss, which is essentially what predictions you're making or calculating versus what's the actual value. And typically for regression problems, you use mean squared error. For classification, we use hinge loss. Next, we use optimization methods, typically gradient descent. A lot of you might be familiar with that. Here we update calculate the gradient, update the weights to reduce the loss. There are other methods such as stochastic gradient descent in order to avoid local minima. There are other optimizers that are commonly used as well. These include root mean squared error, propagation, popularly called RMS prop, adaptive moment estimation, also called ADAM. I've provided a link with more information. The last one is backpropagation. Essentially, the error that you calculate is backpropagated, and you would get the new weight and bias factors. Next, let's look at the typical workflow for deep learning analysis. And this is pretty standard for any machine learning analysis. Here I am showing one for classification. So what is typically done here at a high level? First step is to process the data to create the analysis subset for your use case, and then it's randomly split into training and testing set or validation set. And usually you want to create your validation set depending on how much data you have at hand. So for example, if you have a few thousand samples, you could do a 80-20 split, 70-30, 90-10, depending on your use case. But if you have, say, 1 million samples, you don't really need to do 80-20. You could just leave a few thousand set for validation. The other point I would want to make is validation set is sometimes also called test set. However, what you would want to do is to have test set which is completely different from this split that you are making randomly, to ensure that you have a totally separate data for testing. So essentially you would have training set, validation set, and test set. The training set and validation set comes from a single source which is split. Test set is maybe it could be a different study itself. That helps you build a more robust model and test your model for generalizability. So after you do the second step, which is splitting the data, you would balance your training set to ensure that there is no bias in your data. Essentially, you don't want your model to predict a certain class because it sees more samples of that class. Once you balance the training set, there are multiple methods to balance training set. There's something called SMOT, S-M-O-T-E in R that you can use, but there are multiple resources available that you could look into for balancing training set, or simply you could undersample or oversample depending on your samples. The fourth step is model training, which is where you use a classifier to train your model, and then finally you would do model validation to see your model prediction. For model performance in classification, what we usually start with is to create the confusion matrix, which has this table containing true positive, false negative, false positive, and true positive. And using that, we calculate the accuracy, precision, recall, and F1 score, and also the area under the curve of the receiver operating characteristic curve. One suggestion here, if you are trying to compare multiple models and want to quickly compare which model you want to move forward with and don't want to use multiple metrics, what you can do is you can use the F1 score, which is essentially the harmonic mean between precision and recall. So it could sort of provide you a good sense of how well the models compare to each other. For regression, there are a lot of different performance metrics. A lot of these you might be familiar with. Commonly used in the machine learning space is mean squared error, which is essentially subtracting your actual and your predictor value, sum of squares, and then divided by n. We have root mean squared error, mean absolute error, and R square. So here n is the number of samples, y is actual value, and then y dash is prediction. Finally, I would like to go over some resources that will help you with your gaining a better understanding of how to apply and provide you resources. So in terms of common programming languages, these are the common languages that are used. Among this, the most popular is Python. So there was a survey that was conducted by Kaggle in 2018. They found that Python was the most popular language used for machine learning, followed by R, and then SQL. And then within R and Python, there are multiple libraries that help you with implementing your algorithms. The most popular is scikit-learn in Python, and TensorFlow, which is specific to deep learning. And then there's Keras as well. In terms of the front end, there is RShiny, which you might be familiar with. With Python, there is something called Flask that can be used to generate dashboards for the machine learning models. What I would highly encourage is to code from scratch before you try a package. This book is essentially a good resource when it comes to learning deep learning from scratch. It will help you understand what's under the hood of these models and help you with creating the building blocks, the functions that you would use to create more complex deep learning models. There's information of building CNNs from scratch and also LSTMs and RNNs from scratch with time series analysis. Other AI/ML resources that I would recommend is the data mining book from Witten, Intro to Statistical Learning by James and Group, Elements of Statistical Learning by Hasty and Group. These all provide good background, good fundamentals to build understanding of AI/ML. In terms of deep learning, I would recommend Deep Learning by Goodfellow, Deep Learning, a Practitioner's Approach to Deep Learning by Josh Patterson and Adam Gibson, and then Francois Collet, Deep Learning with Python. There are specialization courses that are available as well. One of my favorites is the one by Andrew and G called the Deep Learning Specialization. It is a specialization that has 5 courses, and they are very comprehensive in case anyone's interested in that. Thank you.